Hi guys, welcome to day 6. So I'm going to go over some homework problems like usual, and then I'm going to introduce yet another way of understanding instantaneous rate of change. We've already got a lot of different ways of looking at it, and today I'm going to introduce another one, a graphical one, a visual one. But let's start by going over a couple of the problems from yesterday's worksheet. So I'd like to go over numbers 2 and 3. And I'll share my document camera here and we'll just go through them. So number 2, we are given the function, let's see, it's the function g of x is equal to 3x squared. And what I want is, it says find the derivative of the function g at 4. So I want the derivative of g at 4. Symbolically, using symbols, that's g prime of 4. That's the collection of symbols that we use to represent the derivative of this function at 4. Now, what does that really mean? That's the instantaneous rate of change at 4. That's what that means. Remember, derivative at 4, instantaneous rate of change at 4, they mean the same thing. So I just need to find the instantaneous rate of change at 4. And, I've got a formula for that, right? So g prime of 4, the thing I'm looking for here, it's going to be given by the limit as x approaches, well, it's always x approaches c, right? C is the point at which you're trying to find the instantaneous rate of change. So it would be the limit as x approaches 4, g of x minus g of c, c being 4 in this case, over x minus c, which is x minus 4. Okay, so I'm just using that formula we've used a bunch of times, except, c is 4, because that's where I'm trying to find the derivative. So I just need to evaluate this thing. So what is this? Limit as x approaches 4. Okay, so we have g of x, and what is g of x? Well, it's 3x squared, right? So 3x squared minus g of 4. Okay, well, what's g of 4? That's what you get when you plug 4 into this function. So 3 times 4 squared, square the 4, that gives you 16. Maybe I'll just do the work over here. G of 4 is, of course, going to be 3 times 4 squared. 4 squared is 16. Remember, order of operations, you want to square this first. That's 3 times 16, which is 48. Okay, so g of 4 is 48. So the numerator of this formula is going to be 3x squared minus 48 all over x minus 4. Okay, so this is an algebraic limit. It's a limit that we're trying to evaluate with a formula. Technically, you should try plugging this number into this thing, right, and see what you get. Because if you get a nice number like 2 or 3, then that's the value of the limit, and there's nothing else to be done. But I promise that if you plug 4 into this expression, you're going to get 0 over 0, right? As you do so often in these problems, which means, of course, that we have to simplify this expression, right, before we plug in the 4. So how can you simplify it? Well, as is often the case, the numerator can be factored, right? So this is going to be limit as x approaches 4. There's a common factor of 3 that can be removed from both terms. 48 divided by 3 is 16, all over x minus 4. And then this expression in parentheses, the x squared minus 16, that can be factored because it's the difference of 2 squares. So it's going to factor as x plus 4 times x minus 4 all over x minus 4. And then you see that we've got a common factor of x minus 4, which can be canceled. So this one here and this one here, those can be canceled, which means that we're going to be left with the limit as x approaches 4 of 3 times x plus 4. And now if you plug in 4, you should get like a nice number, right? If you plug 4 into this thing, you'll get 3 times 4 plus 4. So, which is just 3 times 8, which is 24. Okay, so that is the derivative of the function at 4, or if you like, the instantaneous rate of change at 4. That's how quickly the function is changing at x equals 4. Okay, so that's number 2, pretty straightforward problem, I hope. And then number 3 is a table problem. I did, one of these in the lesson in the video yesterday, but let's take a look. So I'm going to switch back to, I'm going to share my desktop so that we can have a look. So here's number 3. Here's the table. It says the population of Sunnydale, California from 2002 to 2010 is shown in the table. And we've got these different values. Part A says approximate the instantaneous rate of change of the population in 2007. So, remember, I mentioned this last time, but, the instantaneous rate of change, we have a formula for it, right? It's that limit formula that I just used in number 2, limit as x approaches c, blah, blah, blah. But to use that formula, you need to know the formula for the function that we're talking about, right? You can imagine that the population is some function of time, right? Like these are the input values, the x values, and then these are the values of the function. And if we had a formula for the population, like if we knew that the formula for the population was 3x squared plus 2x or something like that, then we could actually use that limit formula to find the instantaneous rate of change exactly. But because we don't have a formula for this function, all we have is a few values of the function. All we can do is approximate it. That's the best that we can do. And how do we approximate it? Well, the idea, of course, is that the average rate of change over an interval will approximate the instantaneous rate of change of the function at a point inside of that interval. So we want to approximate the instantaneous rate of change in 2007. So there's lots of different intervals that contain 2007, like, for example, 2002 to 2010, that contains 2007, and there are others. But remember what I said last time, you want to make sure that you use as small of an interval as possible, and ideally with the point in question in the middle of the interval, right? So that leads us to the interval 2006 to 2008, because that has 2007 right in the middle, and it's the smallest such interval, right? Which means that if we take the average rate of change of this function over this interval, that will be the best possible approximation for the instantaneous rate of change at 2007. So all we have to do is compute the average rate of change, AROC, over this interval. So it's the change in the value of the function. So, this guy here minus this guy here over the change in x, so that's 2008 minus 2006. If you do that, you'll get your answer. So I wonder if I put the full answer there. Yeah, 361.5. So that's what you should get if you take this number minus this number divided by this number minus that number. And that'll give you the average rate of change. Yeah, okay, so I think that's enough for the homework review. There's a bunch of, I know there's lots of other questions here, like AP questions. This is actually kind of like older stuff, right? It's like material from the first few days of the AP of the calculus preview. So if you're stuck on those, then you should like refer back to your notes or the videos or worksheets from those earlier days. It's all about sort of graphical limits and stuff like that, and continuity and that sort of thing. But as always, feel free to send me an email if you're stuck on something. Okay, so let's put this away. And so today, I told you that I would introduce yet another interpretation of the derivative, right? We've sort of already got a lot of ways of seeing it. Instantaneous rate of change, the derivative at the point, that limit definition, they all mean the same thing. And today I'm going to introduce another description of it. So I'm going to begin by taking a look at the following situation. Here I have Desmos, and I wrote this little app basically to draw a sort of nice picture for you. Here's what I have. So first of all, I have some function. It happens to be It happens to be 1/8 x squared, although it doesn't really matter exactly what the function is. It's just some parabola. Here it is. And then I've got some point, which I'm calling c. I think it happens to be 2 in the picture, but it doesn't really matter what it is. Let's just call it c. And then, of course, I have the value of the function at that point would be f of c, right? So this is a graph of f. The value of f is what we call f of c. And here's my objective. I would like to know the slope of the tangent line going through this point. Okay, so just very quickly, what does that mean? This line right here, this dashed green line, this is the tangent line to the graph at C. A tangent line, you might remember from geometry, that just means that it like just nicks the graph, like it just goes through one point, right? It just hits that one point. As you can see, it only crosses the graph at that one point. And my objective is to find the slope of this line. Or really my objective is to find a procedure which will allow me to find the slope of that line. I don't care about the slope of this particular line. What I want is a procedure that in general will allow me to find the slope of any tangent line that I want. So this turns out to be a pretty interesting problem. It took a long time for people to figure out how to do it, and it requires calculus. So here's the idea. I want to find the slope of this green line. You know, what is it? How can I find it? I mean, I know that you can just sort of look at this green line and say, oh, it looks like it's 2, or it looks like it's 1/2 or something. Okay, fine. But you know, if I move C, then I want a general procedure that will always work, not just by looking at the grid. So how do you find the slope of this thing? Here's the idea. What I'm going to do is I'm going to consider a nearby point. I'm gonna turn it on in a second, but I'm gonna enable another point that's just sitting over here. Okay, I think it's gonna be over here, and it's gonna be called x. It's just gonna be some nearby point, close to the point that I'm actually interested in. So I'm gonna go ahead and turn it on now. There it is. So I've got this nearby point x, which is close to C, right? And as you can see, I've also highlighted the point on the graph corresponding to x, right? So this would be f of x. All right. And, why would I do that? Here's the idea. What I'm going to do is draw the line from this point here, f of c, over to this point here, f of x. I'm just going to connect those 2 points with a line. There it is, the blue line. Okay. And you might wonder, why would I do that? Here's the idea. Right now, that blue line is not very close to the tangent line, right? They're quite different. The green line has a smaller slope, as you can see. These 2 lines are quite different. But if I take this point x, this nearby point, and I drag it closer to C, watch what happens to the blue line as I do that. So I'm going to click and I'm going to drag the point x to the left. I'm going to bring it closer to C, and just pay attention to the blue line as I do that. Okay, so it's getting closer and closer. And now, do you notice now that the blue line, which is still connecting these 2 points, f of c and f of x, do you notice now that the blue line is a lot closer to the green tangent line? It's closer, right? And if I drag x yet closer still to C, then you can see that the 2 lines begin to look really close, right? In fact, the closer that I bring x to C, the closer that this blue line gets to the green tangent line, okay? So you might be wondering, like, okay, that's interesting, but like, how does that solve the problem? Remember, my objective is to find basically a formula for the slope of the green line. So why am I even looking at this blue line? Here's the idea. I actually know a formula for the slope of the blue line. It's actually pretty easy to write down. We can actually write down a formula for the slope of the blue line. Because if you look, we've actually got 2 points that are on the blue line. There's this one right here, right? The one that's located at f of c. And then there's this one right here, the one at f of x, okay? And if you've got 2 points on a line, then you can find the slope of the line. It's just rise over run, right? It's the change in the y coordinate over the change in the x coordinate between the 2 points. So let me go ahead and do that. I'm going to open up Microsoft Word so I can type equations there, so I'm not switching between 2 screens. So what is the formula for the slope of the blue line? Well, let's think about it. So slope of blue line is going to be what? I mean, in general, the slope of any line is just, it's rise over run, right? It's the change in the y coordinate between these 2 points divided by the change in the x coordinate. So what are those things? So what's the change in the y coordinate? Well, look, the y coordinate of this point here is f of c, right? Because remember, this is the point on the graph of f, right? F is this red curve right here. This point is actually on the graph, and it's the point on the graph above c. The y coordinate of this point is f of c. It's the value of the function at c. Okay, I just want to make that absolutely clear. Let me just hide this other stuff for just a second. We got this point c, and we've got this function f, right? The red curve. And then this point is the point on the graph of f above c. What's the y coordinate of this point? It's the value of the function at c, right? It's f of c, okay? So just to make that clear. So the y coordinate of this point here is f of c, and similarly, the y coordinate of this point here is f of x, okay? So what's the rise? Like, how high do you have to go up, right? To get from here to here? Well, it's just the difference in the y coordinates. So that would be f of x minus f of c, right? That's the change in the y coordinates. Okay. And then what's the run? Like, what's the horizontal distance between these 2 points? Well, the x coordinate, like the horizontal coordinate of this point right here is c, and the x coordinate of this point right here is x. So the run, like the distance from here to here, is just x minus c. Okay. All right. So that is the slope of the blue line, f of x minus f of c over x minus c. That might be looking a little familiar. But now, remember, my goal is not to find the slope of this blue line. My goal is to find the slope of the tangent line, which is the green dashed line, right? Try to make it dashed, for all the colorblind folks out there. So slope of the tangent line, that's the dashed line, is going to be what? So here's the idea. As I bring x closer and closer to c, the blue line turns into the green line, right? As I bring x closer and closer to c, the slope, therefore, the slope of the blue line becomes the slope of the dashed line. Does that make sense? As I bring x closer and closer to c, the slope of this blue line turns into the slope of the tangent line, which is the thing that I want. I want the slope of the tangent line. So what I have to do is, this is a formula for the slope of the blue line. And to make this slope turn into the slope of the tangent line, what I have to do is let x get really, 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 really close to c, closer and closer and closer and closer and closer forever. And the way to make that happen is, of course, to use a limit. You want to take the limit as x approaches c of this expression. Okay, and that will give you the slope of the tangent line. right? So this right here, this is a formula for the slope of the tangent line at the point C, okay? And we've derived it using geometry, but hopefully you've noticed that this expression here is in fact exactly the same formula that we've been using for the derivative, for the instantaneous rate of change, okay? So what this is telling you is that the instantaneous rate of change of this function here at the point C, instantaneous rate of change at C, is actually the same as the slope of the tangent line at C. So I said that I was going to give another interpretation of this notion of instantaneous rate of change, and here it is, right? Instantaneous rate of change can also be interpreted as the slope of the tangent line at that point. So there we have it. So we have yet another interpretation, right? We have yet another interpretation of this notion of instantaneous rate of change, or excuse me, the derivative. And so, just to be absolutely clear, I'm going to open up today's worksheet. Just to be absolutely clear, because I don't want anybody to be confused, all of these things mean exactly the same thing. Instantaneous rate of change of f at C, derivative of f at C, and now we can say slope of the tangent line to f at C, f prime of C, and finally this formula here, they all mean exactly the same thing. This formula here is a formula for all of these things. They're all the same concept, okay? There's even going to be one more of these. I'm going to give one more sort of algebraic formula for this concept, the instantaneous rate of change or the derivative, whatever you want to call it. Tomorrow, I'll give it to you tomorrow. So that's fine. Now, what I'd like to do now is the following. Now that we know that the derivative at a point, or if you like, the instantaneous rate of change at a point, now that we know that the derivative at a point is actually just the slope of the tangent line at the point, this actually allows us to approximate derivatives just by looking at the graph of a function. Okay, just by looking at the graph of a function, you can approximate the derivative, that is the instantaneous rate of change, at a point. Okay, and here's how. Okay, so here I have the graph of some function. It's again some kind of parabola, a different one from before. Okay, and as you can see, I've highlighted a point on the graph. It's the point sitting above x equals 1. And I have also drawn the tangent line at that point. That is the line going just through that point, that just nicks the graph at that point. And now suppose that I asked you, without telling you the formula for this function, right? Suppose I just gave you the graph of this function and I said, approximate the derivative at 1, or alternatively, approximate the instantaneous rate of change at 1. How would you do it? Well, now that we know that the slope of the tangent line is the derivative, we can actually answer that question, okay? Because as you can see, the tangent line, I've drawn it right here, it appears to have slope 2. There's no way to know for sure, but certainly it looks like the slope is about 2, right? Over 1 up 2. Okay, so since the slope of the tangent line at 1 is 2, that means the derivative at 1 is 2. Or if you like, the instantaneous rate of change at 1 is 2, okay? Or suppose I asked you, what's f prime of negative 1? In other words, what's the instantaneous rate of change at negative 1? So how could you answer that? Well, what you could do is just, to the best of your ability, try to sketch the tangent line at negative 1. Okay, so here's negative 1, and the tangent line, we want the tangent line going through this point right here, okay? So what does it look like? Well, it's hard to draw perfectly. It helps if you have a ruler, but you don't need one. So it looks like the tangent line would be maybe something like that, right? That looks about right. And then we can just ask, approximately, what does the slope of that line look like? Well, very approximately, it looks like it goes down 2 and over 1. We're pretty close to that. Okay, so down 2 over 1, that's a slope of -2. So we could say that the derivative at -1 is -2, or if you like, the instantaneous rate of change at -1 is -2, because all these things actually just mean the slope of the tangent line. Or one more, if I asked you, what's the derivative of f at 0? Equivalently, what's the instantaneous rate of change at 0? Well, to answer that question, you look at 0, right? You look at the point on the graph. Here it is. Okay, you look at the point on the graph, and you just do your best to draw the tangent line. Okay, so the tangent line in this case, I think would actually be horizontal, right? Like I think it would be flat, like this. So that would be the tangent line at 0. And what is the slope of that line? Well, slope of a horizontal line is 0. So actually, this guy right here is 0. The derivative at 0 is 0. The instantaneous rate of change at 0 is 0. Okay. So if I ask you to approximate like the slope of the tangent line, then you just draw. If I ask you to approximate the derivative, that is, if I ask you to approximate the derivative, then you just draw a tangent line at the point of interest and then do your best to estimate the slope. Okay, so let's move on to a little bit of a harder problem, and this is the last thing that I'll do in today's video. I think I want to change to a different color though. So here I've got the graph of some function. I don't know what the formula for this thing is. No idea what the formula is. All I have is a graph. And I'm just asking a few questions about it. So it says, where is f prime positive? Okay. Well, f prime, that means the derivative, right? F prime means the derivative, the instantaneous rate of change. And as we just saw, that's the same thing as the slope of the tangent line. So asking where the derivative is positive is the same thing as asking where the slope of the tangent line is positive. So where is the slope of the tangent line positive? The first time that you try problems like this, it's going to be hard for you to see it just by glancing at the picture. So what I recommend is that you just draw some like sample tangent lines and think about their slope. Okay, like maybe I'll start right here. Okay, pick this point. This is the point sitting above -7. Is the slope of the tangent line here positive? Let's think. The tangent line would look like, I don't know, maybe like this or something, right? Is that a line with positive slope? No. So the derivative is not positive there. Okay, so it's not positive at -7. How about here at -6? Well, slope of that guy, slope of the tangent line there looks like it's still negative, doesn't it? So not there. How about here? Tangent line would look something like this. Is the slope of that line positive? No. How about right here? I think the tangent line there would look like this. Is the slope of that line positive? I think it actually would be 0, right? The slope of the tangent line there would be 0. But then finally, once we move past this point, right? Once we move past this point, we pick a point like over here. Think about the tangent line there. It looks something like this, doesn't it? Okay, and the slope of that line is positive. So the derivative is positive there, okay? And similarly, up here, right? If you draw the tangent line, that certainly looks positive, right? All the way up until, I think right here, the tangent line there is flat again. So I think the derivative is 0 at that point, right? And then after that, I think the derivative becomes negative again, right? Like over here, if you look at the slope of the tangent line, it looks like this. At that point, the derivative is going to be negative again, okay? So where is the derivative positive? I think that it's positive starting basically from here, right? Once you pass this point, all the way up until like here, right? So so what is that range of values? I don't know. I mean, it's hard to know exactly what it is. You know, this point is obviously somewhere between -4 and -5. Let's just say approximately -4.5. That's this point right here, up to whatever this point is. Let's say approximately 1.5. And that's where the derivative is positive, okay? By the way, in the example, I actually write the interval this way. You know, interval notation with parentheses, this expression here where I put it in parentheses, that's not a point. I want to be clear, that's not a point, that's an interval. It means all values from -4.5 to +1.5, not including the endpoints, not including -4.5 and 1.5. That's what the parentheses mean. You might remember that, you know, there's a difference between like brackets, right, in interval notation. Brackets like include the endpoints, like the boundary points of the interval, but a set of two parentheses do not, okay? And I think I don't want to include the endpoints here because I think actually the derivative is 0 at those endpoints, not positive. So that's why I used the parentheses there. So just don't be confused. This is an interval, right? It's not a point, even though the notation is the same. Yeah, and I think if you read, you know, the description, there's a bit more here, but it's pretty similar. Where is f prime negative? I mean, it's negative all along here, right? It's negative all along here. And that's running all the way out, it seems, from -infinity, so all the way over here, up to -4.5. So that's why I have that interval here. And then, of course, you know, it's negative again, I think, all along here. That runs from +1.5 approximately all the way up to +infinity. So that's why I wrote this interval here. Now, and then I say, where is f prime 0? We kind of already answered this, but you know, f prime is 0 when the slope of the tangent line is 0, right? I mean, and tangent line having slope 0 means it's horizontal. So where is the tangent line horizontal? It's got to be, you know, it's got to be right here and right here. Okay, so that's where it's 0. And then I ask one last question. These are really hard. Where is f prime decreasing? This always really throws students for a loop the first time they see it. And understandably, like it takes a lot of practice to wrap your head around what this is saying. F prime decreasing. The first thing you got to recognize is that I am not asking you where the original function itself is decreasing. That's not what I'm asking. This is a graph of f, right? This graph right here, the red graph, that's a graph of f. I'm not asking you where that function is decreasing, right? That's pretty obvious. It's decreasing like all along here, and then again, it's decreasing all along here, okay? Not hard to answer that question. I'm not asking where the original function is decreasing. I'm asking where is the derivative increasing? Excuse me, where is the derivative decreasing? That's not so easy to determine. What I recommend is that you just start picking points, drawing tangent lines, and pay careful attention to what is happening to the slope, right? The derivative is the slope of the tangent line. So we're looking for places where the slope of the tangent line is decreasing. So if I like, for example, if I start right here, okay, the derivative, the slope of the tangent line is, I mean, I don't know exactly what it is, but it's some negative number. Maybe it's like -2, okay? And then if I move along a little bit further and I draw the tangent line there, it's something like this maybe, okay? And what is the slope of that line? I don't really know, but it's still negative. Now, here's the question. So what is happening to the slope? Is the slope increasing or decreasing? Well, here, the slope is a negative number, like -2. And then here, the slope is still negative, but less negative. Do you see that? Here, the slope is still negative, but less negative. Like maybe here it's -1. So the slope, the derivative, has gone from -2 to -1, which means that over that interval, the slope increased, right? The derivative increased. And that's actually happening. If you look at it, it's still happening here. Like over here, the slope of the tangent line is actually positive. And then here, it seems to be more positive. So if you look at the slopes of these lines, the slope is increasing, starts off very negative, then less negative, then less negative, then positive, then more positive. The slope is increasing over that entire interval. But we want to know, where is f prime decreasing? Okay, so certainly not over this time period. But then somewhere in the middle here, the slope begins to decrease. Okay, it's hard to tell exactly where it happens, but obviously by the time that you get to this point, obviously by the time that you get, to here, the slope is clearly decreasing, right? Because it's positive and then less positive, and then it's 0, and then it's negative. So certainly the slope is decreasing over this interval. Where exactly does it switch from increasing to decreasing? Somewhere in here, maybe. It's a little hard to tell, but just ballparking it, I would say like maybe -1.5, okay? And then it continues to decrease all the way out to positive infinity. That's a hard question. It's hard. And there's some problems like this, even in number 1, where is the derivative decreasing, right? Where is the derivative increasing? That's hard to wrap your head around, because you really have to separate, like where is the function decreasing versus where is the derivative decreasing. It's very hard to disentangle those when you first start doing this, but you'll get good at it, okay? So that's it for today. Good luck, guys.